Dear students, we are here to discuss an extremely useful and versatile laboratory equipment known as cathode ray oscilloscope. Now, during the study of various electrical and electronic systems, you all must have encountered a wide variety of signal waveforms. These signals may be periodic or aperiodic in nature and needs to be displayed as a function of time. Now, the device which allows the amplitude of signals to be displayed as a function of time is called cathode ray oscilloscope, more commonly known as CRO, which gives a visual representation of the time varying signals. The image of the CRO is shown on the right side of the screen here. This CRO is very much similar to a voltmeter. However, the mechanical deflection of the pointer in case of normal voltmeters is replaced by the movement of electron beam against a fluorescent screen in case of oscilloscope that produces the movement of a visible spot. Now this electron beam can be moved or deflected in two directions, the horizontal or the x direction and the vertical or the y direction. Thus, the electron beam moving in two directions can have two-dimensional displays and is therefore most of the times considered as fast XY plotter, where the x-axis typically represents the time and the y-axis represents the time varying magnitude of the input signal. Also, the device is so fast that it can display the signals with very small time period, even in the range of millisecond and the nanosecond. Now, for the understanding of the CRO, the very important part needs to be understood, which is the heart of the CRO. CRT is the heart of the CRO, which is basically the cathode ray tube. This CRT is solely responsible for the generation of the electron beam, acceleration of the electron beam to a high velocity, then it deflects the beam onto a phosphor coated screen where it appears as a bright visible spot. There are main five parts of the CRT as shown below. The first part is known as electron gun, which usually consists of the focusing anodes as well. The second part is the deflection plate assembly, consisting of vertical and horizontal deflection plate responsible for the deflection of the electron beam. The third part is the fluorescent screen that produces bright visible spot. The fourth one is the glass envelope encompassing all the components of the CRT, and the fifth part is the base provided for the external connection to the various parts. This I'll rewrite as the part 4 again to avoid confusion. Now we will look at each of the parts in detail. Starting with the electron gun. The electron gun consists of a thermally heated cathode shown here that emits the electron, surrounded by a control grid having a large negative potential that controls the number of electrons. The intensity of the controls the number of the electrons. This basically, the sole function here is to provide a sharply focused electron beam which is accelerated towards the fluorescent coated screen. Now, the intensity or the brightness of the light emitted from the fluorescent screen due to this electron bombardment depends upon the cathode current I, which is proportional to the momentum of electrons, which in turn is given as the product of number of electrons and its speed. So, the intensity depends upon the cathode current, which in turn depends upon the momentum, which is the product of two quantities, the number of electrons and the speed. Since it's difficult to control the speed, we basically focus on controlling the number of electrons for controlling the intensity. Now, the number of electrons in the beam can be controlled greatly by varying the negative potential on the grid, shown here. Now, how is it possible? Let's see here. We know that electrons consist of negative charges. So, a more negative charge on the control grid will repel the electrons, thereby reducing the number of the electrons and hence the intensity. Similarly, a positive potential on the control grid, that is less negative potential, will increase the number of electrons, therefore increasing the intensity. This negative grid is provided as a front panel control by the name of intensity. So, when you rotate the intensity knob towards clockwise in a clockwise direction, you basically tend to reduce the negative potential and hence increase the intensity. When you rotate the knob in the anti-clockwise direction, you basically tend to increase the negative potential and hence reduce the intensity. This is how the intensity is being changed from the front panel control. However, since the electron beam consists of number of electrons all having similar negative charges, they tend to repel each other. With the result, the beam tends to diverge as it comes out of the grid through a small opening shown here. It tends to diverge and therefore it requires some kind of focusing system so that it can be converged onto the phosphor screen. To compensate for such repulsive forces, an electrostatic lens assembly is provided that basically consists of three anodes, namely the pre-accelerating anode, the focusing anode as shown here, and the accelerating anode, all at very high positive potential with respect to the cathode. But yes, the potential of the center anode, as you all can see, the focusing anode is lesser than the two anodes provided at its either ends. Now, let us see how this focusing is being done with the help of electrostatic focusing system. All the anodes, they are in the form of a hollow cylinder. The pre-accelerating anode, as you all can see in figure 3, is kept at a slightly higher potential than the cathode shown here, so that the beam is accelerated towards it. So the positive potential is the main purpose of providing the positive potential here is to accelerate the electron beam towards the screen. Now, as the beam, however, you can see as the beam gets accelerated, it tends to diverge. As you all can see, it is diverging because of the variation in energy. And so this beam needs to be focused on the screen by an electrostatic lens assembly consisting mainly of focusing anode and accelerating anode. Now, how the lens assembly is working, that can be more clearly seen with the help of the figure 7.4, which is basically the equipotential surface between two cylindrical anodes placed end to ends. If you all look here, the anode at the left side, the left anode, is kept at slightly negative potential with respect to the right anode. Because of the potential difference, the electric field is developed and the direction of electric field lines is from positive anode towards a negative anode. Also, the electric field, as you all can see, is non-uniform in nature. The vertical line shown here represents the equipotential surface which is perpendicular to the electric field lines and is bulging out from the center. We also know that electrons experience the force in a direction opposite to the electric field lines, which means that any electron passing between these two anodes will experience a force in a direction opposite to that of the electric field lines. So the electric field lines are from right to left. The electrons is going to experience a force in a direction from left to right, that is towards the screen, and also it will get deflected in a direction perpendicular to this equipotential surface, these equipotential surfaces. Therefore, any electron entering towards the center of the anode will experience no force at all because of the absence of electric field lines. However, any electrons deviated from the center position will definitely experience the force towards the axis of the CRT. Now, if we go back to the figure 7.3 and refer it back, each junction between the two cylinders acts as concave lens with equipotential lines. So, the electron beam from the cathode passing through this first electrostatic lens assembly will be more aligned towards the axis and will be focused onto the screen as it passes through the second electrostatic lens assembly. This is how the focusing is being achieved with the help of electrostatic focusing system. After the beam has been focused, accelerated, it is allowed to pass through the deflection system, which can position the beam anywhere on the screen. It is shown in the figure on the right side of the screen. The deflection plate assembly of the CRT consists of two sets of parallel plates referred to as vertical deflection plates and horizontal deflection plates. Now, in each of these two sets, one of the plate is grounded and the other, and if you all can see, both the plates are grounded in both the sets. One of the plates is grounded and the other plate is given a variable potential through an external voltage. To apply the deflection voltage externally, an external terminal called the Y input or the X input is made available on the front panel control. Students, here one more important point to be noted is that the vertical deflection plates are kept horizontally so as to allow the vertical movement. Similarly, the horizontal deflection plates are placed vertically to allow the horizontal movement. Now, how the deflection is being taken place, let us see here. Suppose a positive voltage is applied to the vertical deflection plate Vy. This positive voltage will attract the electron in the upward direction, resulting into the upward deflection. Similarly, a negative potential on Vy will deflect the electron beam in the downward direction. Similarly, the positive potential on Vx will attract the electron into the right direction, towards the right direction, while the negative potential on Vx will move the electron in the left direction because of the repulsive forces. Now, the amount of the vertical or the horizontal deflection is directly proportional to the voltage applied at these two plates, the Vx and the Vy. And if both the voltages are applied simultaneously, then the net position of the beam on the screen depends upon the resultant of these two voltages, which means that the position xy of the beam spot is directly proportional to the horizontal and the vertical voltages applied to the deflection plates Vx and Vy respectively. The same can be mathematically represented in the form of an equation here. If you can see here, the first equation, the horizontal deflection is directly proportional to the horizontal deflection voltage Vx, which can be written as x equals to kx into Vx, where kx is called the horizontal sensitivity and is the constant of proportionality denoted in centimeter per volts. Similarly, the vertical deflection given as ky into Vy, where Vy is the deflection voltage and ky is the constant of proportionality known as vertical sensitivity. By mistake I have written horizontal here. It is vertical sensitivity. It is basically the vertical sensitivity. It is the vertical sensitivity and is also expressed in centimeter per volts. Now, After the beam has been deflected, it is allowed to strike the phosphor coated screen to produce a visible bright spot. As shown, this figure of the phosphor screen is shown here on the right side. The screen is coated with a fluorescent material called phosphor, which emits light whenever it is bombarded by the electrons. Basically, whenever the electron strikes the phosphor coated screen, the kinetic energy of the electron is converted into both the light and the heat energy on the screen. There are various phosphors available which vary in color, persistence, and efficiency. One of the most common phosphate is the willemite, which is zinc orthosilicate with traces of manganese. This is the one that is producing the familiar greenish trace that we usually observe on the screen of CRO. The phosphor screen is also provided with an aluminium layer and is known as aluminizing the cathode ray tube. Now this layer is very important and has three important functions. The first one is it avoids the building up of charges on the phosphor, which may sometimes tend to slow down the electrons and reduce the brightness. Secondly, it serves as a light scatterer, that is, when the beam strikes the phosphor with aluminized layer, the light emitted back into the tube is reflected back towards the wearer, increasing the brightness. The last and the least, but not the least, is that it acts as a heat sink. Since we all have seen that the kinetic energy of the beam is being converted into both the heat and the light energy, so we need to have a heat sink, and this aluminium layer acts as a heat sink for the phosphor, therefore reducing the chances of the phosphor burning. In addition to all these three parts, we are left with two important parts: the glass tube and the base. All the components of the CRT which we have seen so far are enclosed in an evacuated glass tube called envelope. This allows the free movement of the electrons from one end of the tube to the other end. And it is also provided, the CRT is also provided with a base through which external connections can be made to the various parts, as it is having the external pins. So students, this was all about the functioning of the CRT, whose main purpose is to generate the electron beam, generate and accelerate the electron beam with the help of electron gun, then deflect the electron beam with the help of difflection plate assembly, so that when it strikes on the phosphor coated screen, a bright spot is visible, and the entire assembly is then enclosed in a glass tube for its protection and the free movement, and external connections, for the external connections the base is also provided.